we introduce a deep learning-based tree generator using L-system string. The left is the training dataset and the right are the generated tree models. The key idea of our work is to encode a tree geometry into a hierarchical sequence of letters known as L-system rules that can be learned and used to generate new 3D tree models. To train our deep neural model, we used a large dataset of 30,000 synthetic trees of acacias, birches, maples, oaks, and pines. L-systems encode hierarchical geometry as bracketed strings that are interpreted by a mathematical turtle that generates the tree geometry. L-systems are unfriendly to neural network training. The branches are encoded into brackets that cannot be directly learned because the pairing of brackets would be broken. Also, two elements that are close in 3D may be located far in the string. We introduce a new way of encoding L-systems that virtually eliminates the brackets by putting them at the exact location in the rules. We trace the deepest bracket level in the hierarchy and we encode them as rules. Note the brackets are always at the beginning and at the end of the rule. We repeat this process until there are no more brackets in the given string, ending with bracket-free rules. It also makes the elements that are closed in 3D, close in string sequences. We show that a quantization of up to 95% does not alter the shape significantly. However, it compresses the strings by 44.2% in our experiments. A transformer model based on sequence to sequence is trained for each species: acacia, birch, maple, oak and pine. We encode the rules into transformer tokens. Note that we train the transformer per each level of hierarchy, branching level. The rules are then used to train one transformer per species. Here you can see how the training improves the quality of the output model. Here we show several results of trees generated by our deep neural model. We also validated the tree geometry. We compared the distribution of terminal symbols in the ground truth and generated data. The top row shows the angle distribution and the bottom row shows the distribution of the F symbols for the ground truth data and generated data. The overall average difference is 2.8%. We validated our model by a perceptual metrics. Tree geometry, we validated using tree topology, especially branching distance. We measure the distance by traversing the trees from the root and calculating the geodesic distance of the next branch. Generated acacia, birch and maple trees show the same average distance as the ground truth data, but generated oak and pine trees show 6% and 10% different distances, respectively.